breaking news! Engineers at ECE 2031 Studio unveiled a new ADC peripheral design to bridge real-world analog signals with digital systems. The team focused on simplicity, efficiency, and creating a streamlined interface that makes it easier than ever for SCOMP to process analog data, marking a promising step forward in accessible hardware design. And over to our representative from the team to tell us more about that process.
Our project this semester had the goal of designing an SCOMP peripheral to interact with the analog to digital converter, or ADC chip, on the D10 board. This peripheral should allow for a software to be written to access the ADC's capabilities, adding new functionality to SCOMP. So this is a more visual idea of what we're designing, which is highlighted in red, the ADC peripheral, which, as you can see, connects the ADC, which is on the D10 board, to SCOMP, located on the FPGA. Our solution to this design problem was to convert the output of the ADC chip, which is 12 bits, into a usable version for SCOMP, which is 16 bits. We also decided to focus on the unipolar input ranges, or the only positive input ranges for the ADC chip, which ranges from 0 volts to 4.096 volts. So our peripheral ultimately converts that 12-bit output, which serves as an input into the peripheral, into a 16-bit output, making the ADC output of 12 bits usable for SCOMP. So ultimately, our ADC will send its data to the peripheral. The peripheral will store its value in the data register, which is located at the hex value of C0. And the status register, which is the hex value of C1, indicates when the data is ready. And SCOMP reads the ADC's data using a simple I/O interface, making it easy for users to understand as well as apply for their projects in which our peripheral can be applied. This is our peripheral VHDL, where, as previously stated, we convert the 12-bit output of the ADC chip into 16 bits for SCOMP. To do so, we decided to use a state machine type design in order to shift all of the bits and get the output from the ADC. The initial state of the state machine is an idle state, where essentially we are waiting for the processor to write to the status register, which acts as a start conversation command. Once this happens, we switch into the start conv state, which pulses ADC conv in order to tell the ADC chip to begin converting the analog signal. After this, we switch between the serial clock high and serial clock low states, where we raise the serial clock in order to prepare for shifting the data, and lower the clock in order to get 1 bit at a time from the ADC chip. Once this is repeated 12 times in order to get all 12 bits, and once this happens, we end up at the finished state. And at the finished state, we have collected all of the 12 bits, and this is then ANDed with zeros and put into our data register in order for the user to access the data as a 16-bit number.
Thank you so much for that insight from the project team. This just in, there's a massive tropical storm on the horizon. It seems to be doing massive damage on the coast. For more about that, to the reporter on the scene.
Hello, as you can see, it's quite raining and storming out here. There's tons of sailors out in the sea and all this light pollution. We will not know if they are sending an SOS signal or not. I really wish we had something to help with this.
We should talk to the ECE 2031 team. Maybe they can apply their peripheral to help us in this cause.
With our peripheral, we could perfectly find the solution to this problem and help be looking for SOS signals for anyone who needs it. So for our SCOMP code to apply our peripheral, we have it pull the ADC via the peripheral and then compare the return voltage value to a set threshold in millivolts. If the desired threshold is reached, a state machine is fed each input that passes to detect an SOS sequence. If the sequence is detected, the 505 message, which indicates that an SOS has been found, is displayed on the FPGA. The ADC allows for configurable threshold for discrete signal detection to compensate for different ambient light levels, so that only the strong enough signals are detected and it doesn't waste any energy or time detecting signals that are not any sort of light source they're asking and like searching for help.
So for our demo, we use these switches as representing the dots and dashes in Morse code, which would basically be the flashes of light sending our signal out from the sailors. So then we have switch 1, that is going to be the dots, and then switch 2 is going to be the dashes. We also have a reset button, just to reset to make our testing process simpler, and then we use the potentiometers to basically say, is this a low or a high light signal? And that's basically our way of saying that we're going to count for light interference, and if this was an actual light sensor, we would have obviously a threshold there to make sure that we have no noise taken into account when we're looking for this signal with the lights. So now this is just an example of us going through and putting in our success case. In this case scenario, this is the dots and dash input for SOS. As you can see, the potentiometers are set to our threshold light setting that we set previously. And as you see, we get the 505 message. Now this is just a quick error example showing that nothing changes if we have an error case where the potentiometer is not at the proper threshold values. Finally, this last example is when the potentiometer is in the threshold and the signals being inputted just are not an SOS signal and are not the dashes and dots combination to achieve that. And as you can see, it just keeps resetting once it fails to meet the correct sequence. Thank you so much for tuning in to ECE News. We hope you have a great rest of your day.